Hello and welcome to the presentation of Leaven, a lightweight surface and volume mesh sampling application for particle-based simulation. My name is Alex and I will guide you through the next 15 minutes of this presentation. I start by talking a little bit about particle-based simulation and why there is a need for sampling in it. Then we will take a closer look at different requirements that these samplings should fulfill to be handy in particle-based simulations. Based on these requirements, I will outline the algorithms that are used in Leaven to generate these different samplings. And after that, I will give a detailed demonstration of the Leaven application. In the field of computer graphics, visually plausible simulation is an important topic. Often when we need interactive frame rates, we tend to use particles for representing parts of simulation objects. Imagine if you want to simulate a bucket of water. Simulating each atom will be physically correct but definitely limit your computation power. So we use particles to represent a part of the volume of the water. Simulations often start to get exciting when we start mixing different simulation objects together. Imagine a rubber duck swimming in a pool of water. To simulate something like this, the unified simulation is often desired. Therefore, also the duck needs to be represented by particles. We can spin this idea even further. In unified simulation, often even the boundaries of non-simulated objects, or the main borders, are represented by particles on the surface. This brings us to one question. How to generate such a suitable particle representation or point cloud. This is often a big issue or entry barrier, especially when you're starting with the field of particle-based simulation. This is why we introduce Leaven, a lightweight standalone application to sample the volume or the surface of 3D objects. The application is designed to be easy to use while still being handy for experienced users. Let's take a look at the algorithms used in Leaven. So, as I told you before, in particle-based simulation, surface samplings are often used for boundaries of objects that aren't simulated, like simulation domains, for example. There are a few requirements that a suitable surface sampling should fulfill. So the particles should be distributed exactly on the surface of the volume, so in our case the mesh. They should be uniformly distributed. This is because you want to have the resulting forces that are act on the particles near the surface to be evenly distributed. You also want the distribution to be randomized, because sometimes repetitive patterns in these particle distributions can lead to artifacts. You want to make sure that the sampling is not too dense, just to save some computational power, but on the other hand, dense enough that the simulation particles can't tunnel through the surface. So we require samples to have a minimal distance d. A good rule of thumb is to make this distance the same size as your simulation particle radius. For the surface sampling in Leaven, we use an algorithm originally introduced by Bowers et al., which they use for interactive textured rendering of 3D triangle meshes. This is a grid-based sampling technique. We take the bounding box of the mesh, which is the 3D rectangular box in which the mesh just fits in. We slice this box into grid cells with a side length of our minimum distance d divided by the square root of 3. So the diagonal of this cell is equal to d. We generate a large set of randomized candidate positions that lie on the surface of the 3D triangle mesh. We do this by selecting a random triangle from the mesh, then generating a random position on the triangle by picking two uniform random variables tau1 and tau2 that lie between 0 and 1. With these two variables we generate barycentric coordinates on the triangle. In this way we fill the candidate set with candidate positions on the mesh. Grid cells containing one or more candidates are called valid cells. So, in a number of trials, we pick the final samples out of the candidate set. In each trial, we process each of the valid cells. If a cell is already sampled, or when there are no more candidates for this cell, it can be skipped. Otherwise, we check in each of the neighboring cells if any of these cells already contain a sample that is closer than the minimal distance to the current candidate. If this is not the case, the candidate is a valid sample and can be added to the sampling set. In this fashion, we create the whole sampling set. Now we come to volume sampling. Volume sampling is used to define initial positions of simulation particles. These particles can be used to represent parts of free-moving simulation materials. But as I mentioned earlier, they also can be used for representing rigid bodies in a unified simulation framework. Let's talk a little bit about different requirements we have on suitable volume samplings. If we think of initial positions, it's important that particles don't overlap. When particles in the initial simulation state are squished together, correction forces try to separate them once the simulation starts. Depending on how much the particles overlap, these forces can completely blow up the simulation. But even small overlaps will introduce artifacts. If we want to sample rigid bodies, it's important that they are placed equidistant to each other, so we can ensure an homogeneous density or apply inhomogeneous densities correctly. For free-moving materials, like fluids, gases, or sand, it's important to randomize initial positions. Otherwise, artifacts can appear and propagate through the whole simulation. We take in account these different requirements by having two different volume sampling methods in Leaven. They both have in common that they use signed distance fields for deciding what's inside the volume or mesh and what's outside. A signed distance field is defined by a signed distance function that maps each point of the 3D domain to a positive or negative value. If a point is inside the volume, its value is negative, and if it's outside, it's positive. The magnitude of the signed distance function is defined by the distance between a point and its closest projection to the surface. Creating such assigned distance fields is a topic on its own and beyond the scope of this presentation. The general idea is to fit polynomial functions in cells of axis-aligned hexahedral grids depending on the input mesh. So with this signed distance field, we can decide what points are inside and outside the volume. And let's talk about the two methods. The first method is dense mode. This sampling is used for rigid bodies with an equidistant positions. Here we divide the bounding box of the mesh into grid cells with a cell size equal to the diameter of the particles. For each grid cell, we check if the cell is inside or outside the volume. For cells that are inside the volume, we add a sample at the middle of the cell to the sampling set. The other mode is random mode. This method is used for free-moving materials. For this method, we modify the surface sampling algorithm we talked about earlier. This time, we generate the candidate set by uniformly sampling the bounding box of the mesh. Only candidates inside the volume are added to the candidate set. This time we use a cell size of the diameter of the simulation particles divided by the square root of 3 for the underlying grid structure. The method for picking samples from the candidate set remains the same as in the surface sampling algorithm. Now let's take a look at the application. Once we're in the app, we can load in 3D triangle meshes in the OBJ format. When the mesh is loaded, we see it on the right in the viewing area. We can manipulate the view by arcball rotation with the left mouse button, by panning it with the right middle mouse button, and zoom in and zoom out with the right mouse button. The checkerboard you see on the ground here represents a 1x1 area. When mesh normalization is turned on, the mesh will be scaled to fit inside a unit bounding box with a side length of 1. When mesh normalization is turned off, the original model scale will be used. You can also scale up the model by using a scaling factor. For example, let's make it twice the size. Bring it back down to the unit size. Let's start looking at the sampling methods we have available. We start with surface sampling. On the left here you can see some of the options we have available. Minimum distance specifies the minimum distance between 2 points on the surface. The distance is measured in either geodesic or Euclidean norm. We recommend a minimal distance between 2 points, roughly about the same as the particle radius in your simulation. Furthermore, you can control how many potential sampling points should be generated. A higher density means more computation time and more memory consumption, but also more possible sampling points to choose from. The number of trials specifies how many iterations for drawing suitable positions from the potential point set should be done. Once we hit the sample button here, the sampling is generated. The radius value up here has no effect on the sampling itself, it just has an effect on the visual appearance of the particles in the viewer. So let's turn this down a notch, hit the sample button again, and we see the particles are rendered smaller. Let's do another one. Let's reduce the minimum distance between particles and reduce the render radius a little bit and generate a much denser sampling with more particles. Let me reset that real quick. Now let's take a look at volume sampling. Here the particle radius affects the sampling. It should be the size of your simulation particles, since you don't want to have overlapping particles in your initial sampling. When the invert option is turned on, the volume between the bounding box and the mesh is sampled. Furthermore, the SDF resolution can be increased in all 3 axes. This can be necessary for detailed meshes and small particle radius or a large scale. For volume sampling, we have 2 possible modes: grid sampling mode and random sampling mode. Let's first take a look at grid sampling mode. This will fill your object with grid-based sampling particles. But this order can introduce unwanted artifacts in your simulation when used as starting position for your simulation particles. It can be used though for sampling rigid bodies in a unified particle simulation. Let's take a look at another sampling with smaller particles. You see this more details coming up in this sampling. Let's reset this. The second option is random sampling. The parameters density and trials are the same as in surface sampling, which we already talked about. Creating such a random sample is less prone to introduce artifacts in your simulation when used as starting position for your particles. The algorithm makes sure that no particles will overlap, so no initial forces are introduced to your simulation. Let's take another look at a smaller particle radius. And there we can already see the shape of the object again, but the particles seem to be in no order in compared to the dense mode before. That's all from the demo of our application. Thanks for listening to my presentation. Hope you enjoyed it. Feel free to ask questions and check out the application once it is released.